Hi, everyone who joined our machine learning weekly study jams. And this is the last part of our image classification uh, algorithm journey. Of course, we will study more in details, and I hope we can study more advanced topics. But for the four parts image classification algorithm, this is the last session. And today we're gonna use all the knowledge that we had obtained from the previous 2 or 3 sessions and apply for the rock, paper, scissors problem. That's actually the problem that we have discussed in the first session. So we already know that although it seems like easy problem to classify the rock, the scissors, and paper, writing the algorithm for the machine to classify these forms, hands forms, is actually difficult because we should be aware of the different ethnicity, different shapes, different like decorations or stuff like nails and stuff to train the model to recognize these 3 types of shapes. But we also learned that we can use deep learning and train our model to detect the pixels or the patterns in the pixels, in raw pixels, and then classify these images according to the patterns in the pixels. This is what we have done in the previous session. And how about applying this knowledge on rock, paper, scissors problem? So what we're gonna do first is we're gonna see our data. We're gonna start with data. And I'm going to show you where actually the data comes from. So this is the link for you if you want to do anything later on. We can visualize briefly, explore the data, what is our data here. And we see the different, so this is the rock form. This is different skin types, skin colors, different shapes. Someone holds it tightly and someone holds the hand loosely. And we're gonna download this data set from the resource using this script. And if you don't mind, I'm going to use the presentation maybe in this format. Oh, okay, it's better for me to switch. So we're gonna download the train dataset and the test dataset using this script. And then we're gonna unzip the downloaded files using the library zip file. And we're gonna store this in the temporary directory, like so. So we unzip the first file that we downloaded and the second file. The first file is just RPS, and this is the test data set. And when we download these data, it will be stored in the directories and subdirectories of the specific labeled directories. So for 3 shapes that we are going to classify, we're going to have 3 directories here. And in TensorFlow or in the Python as well, I think there is an image data generator. So what is this? It helps us to create the training and validation data set according to the different types of our classification types without doing much work, because it will separate the files into each categories and number it accordingly to the directory it has been segmented for. So in the end, we're gonna have an image and which we need to classify. And the name of the image is going to be like this: 1, 2, 3 for the rock, and 2, 4, 5, 6, 4, 5, 6 for the paper, for example. This is going to be our labels. So we don't need to actually provide another file with labels. The names of our files will be actually the labels. This is thanks to the image data generator. And this is the code which helps us to create such label data set. We're going to use the image data generator. So we define the directory, training directory, in the temp directory. So this is where we already downloaded the image files. And the RPS is our training data set. So after we initiated or created the image data generator, we're going to use the flow from directory method to create the training data set. We specify here the directory where we want to create our training data set, the target size, which is 150 by 150, and the class mode is categorical. And good thing is that we can also create the validation data set using the same approach. So we use just a different directory, and other things is just the same. Then let's look at our neural network definition. So we know that we already encountered this structure before. We have learned about the convolution and what is max pooling. And here is just four definition of convolution and max pooling. So each convolution has its own max pooling. And then we define the deep neural network as we did in the first session. We first flatten our input, then the dropout is the method to increase the efficiency of our, maybe the accuracy as well of our model. It will do this by excluding some of our neurons. And then the finally, we have the dense layer, and the output is 3. So here, what we need to keep in mind is that previously our fashion minis dataset consisted of about, I don't remember actually, was it like 1,000 or 100 images of different types of shoes, and it was 28 by 28. Now we have bigger images, which are 150 by 150. And we're gonna have 3 neurons in our output because we categorize our data into the 3 types, right? The paper, rock, and scissors. Other things is same for as for the algorithms we have already seen. And when we define our model, now it's time for us to compile it. And here is everything is same. We just use different types of loss and the optimizer, I think, compared to the other algorithms we saw before. And then we feed our data to the model. And instead of using the training set and label files, we're going to use the train generator. I have already described this before. So this is what helps us to get our data labeled when we segment, or how to say, when we distributed our data into validation or training data set, it will name the files according to the types of the directory it is distributed for. And the epoch size here is 25, but we will see, maybe we will use the same. And the validation data is also made by a validation generator. So this is the fitting our model. And to predict how good our model classifies rock and paper and scissors, we're gonna use the predict method and give our model some new images to see the results. And this is just the example of the output that we can potentially see. This is, for example, scissors. We named our image as scissors too, and we see here that it perfectly recognized that this image is actually scissors. Now, I think when you got some surface overview of the image classifier for rock, paper, and scissors, let's try to actually run the commands ourselves and learn in more practical way how to do the image classification. Could you please go to these, hi Abdullah, could you please go to this link, and we're gonna start from the beginning. And don't forget to run the first lines, because it helps to set up the environment. And as I already explained, first of all, we need to download our data. And we're gonna use these commands to download the data from the, I think this one. No, this is the catalog actually of the data. And the source of these images is written in this link. So we're gonna use this Lawrence Morenay block, which stores the training and test data. So once this license under this something is run, we're gonna run this code. Somehow it's busy running, but it's too slow, I think. Let's wait a little more. If you have already received the OK sign, you can proceed with this code. Just run it, okay? If mine will not work, I'll try to actually, I have already run this on my PC, but probably 2 sessions is too much. If it's gonna take some time, let's just go with this tab. I'm going to just explain and see the result instantly. But only in your case, you can see maybe a different result. Tell me if it's different, because I'm actually curious later on what will be the accuracy and how long it takes. So once we run this program, we have our training and test that data set downloaded. Now, because it's in the zip format, we see here, it's in the zip format, we need to unzip it. And we use the OS library to specify the path in our directories. It interacts with our system. And the zip file helps to unzip the downloaded test and train datasets. So here we just define what is our training dataset. We unzip it and we extract to the temporary directory, both the training and test dataset. So you need just to run it, okay? Maybe that's a bad idea, but we just neglect it, like it doesn't run. I hope you can run it on your computer. If you have this check mark, it means that the program has finished successfully and you have no errors. And if you got an error, let me know. We will try to fix it. If you have no errors here at this part, then I will proceed. Otherwise, just freely unmute yourself and say that, oh, okay, we have here a problem. And now we want to maybe visualize or see. So here in the first 3 lines, we have our directories, rock, paper, and scissors defined. And we know what is the path to our directory. So we join the temporary files, RPS, which have been unzipped, and the rock, paper, and scissors accordingly. Now, if we want to see what files are there downloaded into our folders, we just use, like, for example, how many files there. We just use len function and see each directory's list, right? So for example, in my training rock image dataset, we have 840 images, and this is actually the same for other forms, hands forms. And we can list these images as like names. For example, using the print function, rock files, the 10 rock files are here, rock 3, 1, 2, 1, and something. So I think it's gonna be, yes, 9 of them. Or it's 10. Let me see. 1, 2, 3, 4. Yeah, it's 10. It starts from 0 to 9. Okay. Now we visualized what is our data set that we have downloaded. This step is not necessary actually for the training. We just want to confirm that files are there. And now maybe it's better even to go further and visualize these images. We will use the matplotlib library, the image and pyplot, and we specify the number, the index 2, because we want to see just 0, 1, so 2 examples of each hands shapes. So we define here rock, and it will show us the file name, the image of the file name peak index -2 from this to the peak index. So it's practically just 2 images from each shape. And we plot these or visualize this by images show. We don't want to see the axis, and we have the show, plot show to see. So here is the rock, the paper, and scissors. So just 2 examples. I think it's enough. It's the same images we saw here in the source of these images. Now, let's go to the dividing our dataset into the training dataset and the validation dataset. And I'm going to explain a little bit more about this actually later on, if we have time, because I want to emphasize on the importance of this data processing. I myself find out this not that much long before. So we have here the image data generator imported from the Keras preprocessing. So this is the library, and from here we import the image and image data generator. Now, when we defined our directory, and I said in the presentation that we have the different directory for training and validation data set, we then create our image data generator and specify some parameters here. For now, I think it doesn't matter what parameters we're going to use. We just stick with this. And we create the image data generator for training data and for validation. So we here use the same call of the function, right? Now, let's use the flow from directory. This gonna take the training directory, which we specified before, the image size, the target of the image size, but it's the same as images actually we have already downloaded, and the class mode categorical and the patch size 126. So we have the train generator, validation generator. It's gonna generate the images for our rock, paper, and scissors training dataset and the validation dataset respectively. And our images eventually as an output are gonna be labeled by the numbers. Actually, maybe we see it before. So it's gonna be labeled by the numbers that corresponds to the particular directory of the rock, paper, and scissors. And this is our model, as I explained already. Here we have the desired input shape, and it's much bigger than the fashionist dataset. We have the first convolution defined, the second, the third, the fourth. Then we have this is what we have learned from the previous session about the convolution and max pooling. So what this does is we try to detect the features in our images. For example, when we use the fashionist, we I think last time we used the staircase image, and there were some vertical and horizontal lines, and there was some people going up and down, and we want to detect the staircase only, for example. Then we use this convolution and max pooling to emphasize the most prominent features while decreasing the background or some features that are not necessary for the detection. And every time we perform this, our image becomes firstly super blur, but we can actually control this. And the second thing is it becomes smaller and smaller by pooling. So actually, 2 by 2, it means every time we perform pooling, max pooling, it will take the largest value of the neighbor pixel, and by this we extract one maximum pixel value and recreate the image. So every time we perform the max pooling, our images decrease and decrease in the size, and we have a little bit blur or a little bit less prominent background. But together, this helps to not only remove unnecessary features, but to enhance the features we are interested in. And once we've done this, so this is what actually helps us to create a better or more accurate result. Without this, we could use potentially just deep neural networks, but it would be less accurate. So what I want to say is that you can actually try to run your program without these lines and see the result. It would be interesting. Otherwise, we just go into the deep neural networks, and we have the layer Flatten, which takes what we have got from this convolution. And because our size is 150 by 150, we need to flatten it before it goes to deep neural network. And this dropout helps to remove some neurons to get better efficiency. And we have the hidden layer of 512, which is not that important. The important thing for us here is to know that here, last time we had, I think, just one output, or maybe in the in the second session, we had the fashionist dataset, which had the 10 different types of fashion items. Now here we have 3 as an output because we have 3 categories. And we just want to see the summary of our model and compile the model, defining the loss, the optimizer, and the metrics, which is the accuracy, and fit the training data set, which is defined by the train generator. We define the epoch size 25. We can adjust this actually if you are interested. And here is the validation data defined by a validation generator and some other parameters. So if you run this program, you're going to see some description of the model, and this is what actually is interesting. The loss values, the accuracy of your training set, the values for the validation, for the loss and the accuracy respectively. So here you can compare. And once you run this code, if you already done this and you got some numbers, could you please share your thoughts about these numbers? For example, how training loss behaves, how validation loss behaves, what's the accuracy for loss for training and for validation for you? What have you noticed here? If you have not yet seen any numbers, that's fine. We can wait a little bit. Otherwise, if you got, for example, like 3 to 5 epochs, you can already see some interesting things about these numbers. Any thoughts? Any observations? For example, if we look at the loss for the training dataset, we see that the first epoch is equal to 1.2 or 1.3 almost. And then in the second epoch, it is equal to 1, almost 1.1. So it decreased, right? And let's see a little bit further. So we see here it's equal to 0.2. Let's go on further to the last epoch. And we see here it's 0.05 or 0.6. So the loss is decreasing, right? Is it good or bad? Is it predicted? What do you think?
Good.
Excuse me? So as we already learned from the previous sessions, what we are trying to do is we're trying to reduce the loss, right? So actually, we have here loss, which is decreasing at each epoch, which is predicted, right? Or expected. And if we look at the validation loss, we see the same trend here, right? Sometimes it's increasing, so it means, okay, so that's interesting, right? So here we see here it's decreasing then increasing. So what can it mean if the loss suddenly increased? Or like this, for example, or like this. So our goal is to decrease the loss. And why we do this? Imagine we have a concave shape graph, which is the parameters, and we want to, if we had, for example, the simple problem of like linear regression, we want to fit our fit line into the data, and we don't know, okay, should it be like this or like this or like this? So we are trying to adjust our model, which is the linear model, into our data, not so, like drastically, right? Because this we won't be able to find the efficient parameters for our data set to describe it, right? What we're gonna do is we're gonna change our model stepwise, step by step, to minimize the loss, which means to minimize the error. What we have defined here, when we define the model, we define our like the function that estimates the error, right? And what we're trying to do is we're trying to decrease the loss because we want to fit our data more accurately, right? And if we, for example, are reaching to the correct point, at some point, if you have larger descent or larger step size, you're gonna go through your target point, right? And that will increase the loss. So if we have here a stable decrease of our loss, that's a good thing. But for our validation data, although we have some decrease, constant decrease, at some point we see here more towards the end of our validation, we see here that actually the loss increases sometimes, right? So it means we go through the target point. And let's see the accuracy. Now here, the accuracy at the first epoch is equal to 0.3. We go a little bit further and it's equal to 0.8 already, right? Now we go through a little bit more and see it's 0.95, 95% accuracy. It's almost 100% of accuracy, like 98 towards the end of the training of our data. And let's see the validation accuracy. It starts at the same percent of accuracy. Now, as we go through, we see, okay, sometimes it almost reaches the 100% of accuracy, like 95%, 98% of accuracy at the 8th epoch. And then we see here 100% of accuracy. That's unexpected, right? Why it's 100% accuracy? Sometimes it has 87%, which is not that bad, but we see here towards the end, we've encountered the data that has the 0.75% of accuracy. So something is strange here, don't you think? So the validation data set have interesting loss values and interesting accuracy. So from here, we have got some interesting points, and we're gonna remember them because later on we will discuss these important issues. Maybe not that later on, because here you already saw, but you can run this script which uses the matplotlib pyplot, and we're gonna see this results visualized in the graph. And if we look at it, and you can run it on your browser as well, we see here that as our training accuracy slowly but surely increases, the validation accuracy starts, it fluctuates well, right? It reaches the almost 100% accuracy faster, but it has some points where it doesn't classify the data set well. So what can you say about this? If you saw this, what thoughts comes to your mind about our training data set, maybe about our validation data set, or about our model? I think if you are interested to learn machine learning, the coding part is not that maybe so difficult, right? We are trying to learn this, but I don't hear much about analyzing what we receive as an output. So here we use someone's code, right? We're trying to learn this code, but we receive the output. And if you think that this output you can just attach to your report or somewhere in like your resume, this is useless, right? The thing that we are interested is the impact, or the result, what we are using machine learning for. And in our case here, we want to classify paper, rock, scissors. This might be not that great problem for our world problems, right? But it's a good problem to learn the approach and use this approach for maybe bigger problems or more useful problems. And now when you have the paper, rock, and scissors problem, it's a good chance for you to practice the analysis or the observation of the output. So don't be afraid to share your thoughts, like anything that you think about, like what is happening. Maybe you don't know about what is validation, right? Maybe you have not so much knowledge. Maybe I didn't explain to you why we have training, validation, and test data set, right? So any thoughts about the output is relevant. So what we see here is that our model works good on the training data set, right? But somehow when we do the validation, we see here that sometimes it works well, pretty well, even better than the training data set. Sometimes it works bad. And one thing we can say is that maybe during the validation, it encountered some images that the machine already saw during the training. Is it possible? Another thing is maybe our model fits to the particular types of images. So it means that when we run our validation, we do this by like providing images. Actually, we should provide it randomly, right? Without any hidden thought that, okay, I provide exactly this image to you, like to the machine. It means that occasionally we provide some images that are super easily recognized and some are not. So maybe there are some images types that our machine learned specifically to recognize, but some type of images, it has no such good understanding of its concept, right? Maybe we overfit our model to a particular type of the images. And in the last part, you can run your program to test your new images, like to test your model on like any other images on the internet. You can upload here. You can provide your own images. And this is, I think, the point where I wanted to go through the machine learning crash course, which we have started before, because we stopped at the first steps with TensorFlow topic, and the next topics we learned by practicing actually these computer vision algorithms. But I want to provide you more information about what we actually done. The first thing is about the generalization. Let's see the video. Do you hear actually the video? Because I'm in the headphones, so maybe you don't hear. This is the link. I'll try to use speakers.
Machine learning, we're really interested in generalization. Let's dive into that topic a little bit more. So here we've got a data set where we've got some spam examples here on the left and some not spam examples over on the right. If I wanted to, I could try and fit a linear model to sort of disambiguate the spam from the not spam. But any sort of linear model that I would try and fit here would end up making a little bit of error. Maybe this guy would be misclassified, or that guy would be misclassified as being on the wrong side of the line. And I might decide to try and be clever and get 100% accuracy on my training data by drawing a more complicated line. Maybe it would look something like this. I'm going to go and make sure that my model is going to be super clever and get 100% accuracy. All of my training examples are now completely correctly classified. What's the issue here? Well, the issue is, what if new examples are coming in? I might end up with some new examples that the model is just not really well suited to doing a good job on. So in a sense, this model has maybe overfit our training data originally, and it doesn't do a good job of classifying new, previously unseen data. Okay, so we've seen that if our models are too complicated, that overfitting is a real problem. How can we make sure that our models are not overfit in practice? Well, let's step back and take a look at the big picture of what it is we're trying to do in machine learning. At a very abstract level, we can imagine that there's some hidden process that is giving us data. And that hidden process might be something like the process by which emails are generated as either spam or not spam, and people label them as such through their perceptions, or the process by which pictures of puppies are generated and people label them as cute or non-cute. The process could be anything that gives us data. And in general, we're not going to know the full details of that process. The only thing we're going to know is the concrete examples that we get to sample from that process. So specific pieces of email or spam, specific pictures of puppies. We call those samples our data samples. Now, ideally, we would like to be able to train on a data sample and then know that it's going to do well on new draws from that hidden distribution. How will we be able to trust that? Well, one thing that we could do is we could use some nice ideas that go back as far as William of Ockham from the 14th century, our first machine learning theoretician, who developed the idea of Occam's razor, basically saying that a model should be as simple as possible. There's a whole field around this called generalization theory, and it's a fascinating field. We're not going to get into that too much in this course, because we don't have to use theory. We can, in fact, use empirical stuff. And the empirical strategy we can use is to take another draw from that distribution and see how well we do. This is called using a test set methodology. So we pull one draw of data from that distribution, we train on that, that's our training set. We take another draw of data from that distribution, we call it our test set. And if we do a good job, about as well at predicting on our test set as we do on our training set, then we got a pretty good feeling that our model is going to be able to generalize well onto new previously unseen data. Now, there's a couple of caveats here. This is sort of the fine print of machine learning. The first is that we are drawing our data, are drawing independently and identically from that distribution. We're not biasing ourselves in any way. The second is that distribution is stationary. It doesn't change over time. And the third, kind of implied here is that we're always pulling from the same distribution. We don't suddenly start pulling from a different one. Now, those are critical assumptions, and they sort of form the bedrock of a lot of what we do in supervised machine learning. But in practice, sometimes we do violate them. The stationarity assumption might be violated if, say, user behavior on shopping changes over the holiday season versus in the summer. And the pulling from the same distribution might change if people suddenly decide that a different breed of puppies is cute than they saw before. Fashions do change. So it's important for us to be aware of these assumptions and also to pay careful attention to our metrics anytime we know that these assumptions might be violated.
So according to this video about the generalization concept, we can understand that, okay, so maybe our model is not that good because it works well for the training data set. It learns the concept of some images, some forms of hands pretty good. But when we provide some validation data set, it works not that stable. It's not that stably accurate, right? And according to this video, we understand that, okay, so we need to test our model using the test data. And we actually didn't do this today, but imagine we are performing the training and we provide the test data, which is not labeled. For example, I'm not even sure what is the paper, the rock, or scissors. I am blindly providing the data, and I see that, okay, so I provided some like 10 data and 10 images, and I see, okay, sometimes it predicts correctly, but sometimes not. And the accuracy is in general like 89%. So, or maybe even worse, right? Sometimes it's 100%. So what we should know about the training and test sets? Let's see in the next video.
Okay, let's talk a little bit more about that test set training set methodology. Now, what will happen if we only have one data set to work with? For example, we've got one big draw from our hidden distribution. Well, one thing we can do is we can divide that large data set into two smaller sets and use one for training and one for test. We need to keep them separate. It's also probably important to make sure that we do randomization before we do that splitting, so that we don't, say, by accident, end up with all of the winter data in our training data and all the summer data in our test data. That would be bad. Now, how large should we make our different splits? Well, these are two things in tension. The larger we make our training set, the better model that we're going to be able to learn. The larger we make our test set, the better we'll be able to have confidence in our evaluation metrics. We'll have tighter confidence intervals. If we have a very large data set, things are good. If we've got 1 billion examples, we might be able to still hold out 10 or 15% for a test and have strong confidence intervals there. If we have a very small data set, then we might need to do something a little more sophisticated, like cross-validation. Now, there is one classic gotcha that's worth bringing up, and this is that you do not ever want to train on your test data. This will give you unrealistically strong opinions about how good your model is. In particular, If you ever find yourself on that magic day when you have 100% accuracy on your test data, double check that you have not made a mistake and have accidentally trained on your test data. This can happen. It happens to everybody at one point or another. So before you celebrate and throw a party, double check your data.
Okay, so we know from our previous example of rock, paper, and scissors that we hope that we actually don't know much about the data set that we have downloaded, right? We saw briefly, but maybe some images that we provide for the training and the validation are actually same, and that's why they give us 100% of accuracy. So as he says, the instructor, if we have the 100% accuracy, then it's good to check out our data, right? It doesn't maybe mean that it's wrong, but it's not highly likely that you got so good 100% accuracy. And we learned from the previous sessions that usually it's not gonna be, for example, if we do some integer to integer correlation analysis, it's not gonna give us the exact value how what is the relationship between x and y, like for example 3.0, right? Because it will give us the probability that this relationship between x and y is equal to 3 point something something something, because it works with the probability. So the probability of getting the 100% accuracy on our validation of this data is not that big, right? So we should be always aware of this when we see the results, the output of our training process. Now we know about our training data set and the test data set that we can train and then easily test how good our model works. Let's learn a little bit more about the validation, what it is. First, I want to ask you about actually this problem. So we know that we can have the test set and training set and iterate over and over again to develop efficient model. For each iteration, we train our training data and evaluate on the test data according to these videos. And using the evaluation results on the test data to guide the choices, what we should tune in, right? What hyperparameters we should change to get the better results. Is there anything wrong with this approach? So practically, we saw that there is a training data, the validation step, and then we haven't done it, but we have the test data. We can, or our purpose is actually to test on the test data, the unseen data. But as we go through this machine learning crash course, they first tell us about the generalization, that we don't want to have overfit model. And to do this, we should always check our training set with the test set. But at this step, something is wrong. What is this? Is it because it's computationally inefficient? Is it because doing many rounds of this procedure can cause us to fit some particular features of our specific test set? Or it's okay, nothing is wrong with this approach? What do you think? I think computationally inefficient is not the correct answer, right? Because we know that people can do complicated models. We can analyze big amounts of data. So doing this usually is not that inefficient. But we also know from practical experience that we had with the computer vision basic models. We know that it's not totally fine because we used training and validation and then testing, right? Then it means that the third answer is not correct. So the correct answer is that doing many rounds of training and evaluating on the test data might unpurposely gives us a machine that is trained to recognize, for example, specific types of images. So this one is the correct way of approaching this method. And lastly, let's learn a little bit more about validation and how to approach our data set.
So now we have this powerful test and training set methodology. So let's imagine that we're using it in practice. We've got our test set, we've got our training set, we did a good job of separating them out. And we're gonna now do some iterations. I'm going to train a model on my training data, I'm gonna test it on my test data, and I'm gonna observe its metrics. And I'm gonna tweak the learning rate or something like that. I'm gonna try again and see if I can improve my test set accuracy. Maybe I'm going to add some features in. I'm going to take those features out and keep iterating and iterating till I find the best possible model that I can based on my test set metrics. Are there any problems here? Well, one thing I could imagine is that maybe I'm starting now to overfit to the peculiarities of my test data. That's too bad. So here's another way to handle that. I can create a third data set out of my partitions. I'm going to call this my validation data. And I'm going to use a new slightly augmented iterative approach where I'm going to do my iterations by training on my training data and then evaluating only on my validation data, keeping my test data way off to the side and completely unused. I'm going to iterate and iterate, tweaking whatever parameters or making whatever changes I want to my model until I get very good data, very good results on my validation data. I'm then and only then going to test my model on the final test data. And I'm going to make sure that the results that I'm getting on the test data basically match what I'm getting on my validation data. If they don't, that's a pretty good signal that maybe I was overfitting to the validation set.
Yeah, so this is actually controversial, right? So if you have the validation set and your results of the test set are not that similar, then maybe you are overfitting to the validation set. So we need to keep in mind that we can still encounter overfitting problem. And to maybe check our understanding of this, or to have more practice, more practical knowledge, this is the collab that I encourage you to do. If you think that you're not going to do this on your own, we can leave this to the next session. Otherwise, in the next session, let's talk more about our data set, how to prepare it, because we already started to do some algorithms. Maybe you want to know more about the data preparation, data processing, and then apply, for example, the classification problem, right? So we already know how to do this. Maybe we can now focus a little bit more on the data. So if you're not going to do this exercise, we might do this in the next session. Otherwise, I will try to also prepare some information, some practice about the data preparation and data processing. And this is the end of the study jam. I hope you learned some new information and want to try on your own to run these algorithms. And I hope to see you next week, maybe, yeah, on Friday. So Have a good weekend. Bye-bye. Bye, Benny.